Okay, yeah, the recording has begun.
Okay,
Over
thank
to you.
you, Dr. Kalyan. So, welcome all of you to the session, first session of day three. So, I'll stop my camera here and I'll share my screen. Okay, so I hope my screen is visible.
Yes.
Okay, thank you. As you can see, I have slightly changed the title of this topic, but the content is same. I rename the title as security attacks on memory systems. But actually, by the term memory system, the meaning is I'll cover the concept of cache, NOC, and main memory. So the content is same, only the title is different. So security attacks on memory systems, part one is I'm now talking. So this is a 2 hour lectures, and the part two will be discussed on session one, day five. So the first slide here, I'll explain the aim of this talk. The aim of this talk is to motivate the audience to do research in this area. So our main aim here is to such that after this FTP, at least all the participants can get a starting point from where you can start doing research in this area. Since this is a faculty development program, so most of the participants here are faculties. And we all know that the research is a very important part of our career. So this is our aim here is that at least you can get a starting point from where you can start doing research in this area. Those who are already working in this area may also get get a new direction, new problem statement from this talk. But actually, the mainly when I have designed this talk, I was mainly focused for those who want to give a fresh start in this area. So most concept that I will discuss here, most of the concepts are actually basic concepts. Yeah, and one important point here is please note that the concept that I will discuss here are basic concept, and these I am only explaining to introduce the entire this area to you and to motivate you. It may be possible that some of the recent research work I'll not cover, or it may be possible that some more interesting developments are already there in the literature, and I may not cover all these things, though I'll cover some existing works, some literature works. But I hope you also understand that covering all the existing works and all the recent development is not possible. So the main aim is I have written here is to motivate you. Okay, so this is the outline of this talk. Outline here today. First, I'll discuss about the introduction to security attack. From this is day three, so first 2 days and maybe today also. In all the sessions, we are discussing about different security attacks. So what I have done here, I have tried to categorize this attack in 2 3 categories that I will explain, and then I will explain say a specific attack on main memory. So this first two part, this part I'll explain. This is part one, and then in part two I'll explain attacks on-chip components. Basically, on-chip component means cache memory and network on chip. So all this is actually part two that I'll cover on last day, session one. So if I concentrate on part one, then if I want to discuss about attacks on main memory, then first I need to explain what the basic concept of main memory, what is the structure of a main memory, how main memory works. Without this, I cannot start with a attack. So today's first part mainly, first hour I'll mainly concentrate on this part, explain the basic structure of a main memory, and then the next hour I'll discuss about raw MR attack. This is a attack on main memory. And the second day, you can see I'll discuss about basic on-chip components like cache memory, NOC, all these components I'll discuss, and then I'll discuss about side channel and covered channel attack. Why I'm not discussing side channel and covered channel today? Because I think tomorrow there is a talk on side channel attack. So I'm waiting for that talk. So I hope that most of your basic concept regarding side channel attack and all will be cleared on by tomorrow. That's why I moved the this part, attack on chip component part, to the last day. And I'll also discuss about NOC and hardware Trojan. That I think it also discussed yesterday by Dr. John. And on part two, I'll also explain quickly that how to start research in this area. That, as I have mentioned, that I will try to give you a starting point. So that starting point I'll discuss in part two again, and I'll quickly explain or quickly discuss the current research who are going on in my lab related to security. So the knowledge required to understand this talk is the basic concept of computer architecture. Though I'll try to cover all the basics, but it may require some basic knowledge, very basic knowledge, and also previous lectures of this FDP. This second point is not important for today's lecture, but for my part two, this point, previous lecture of this FDP is very important. So all the lectures are being recorded, so you can watch at least the lectures where the basic concept, see the concept that I have explained, that I've written here, are already covered in this FDP. Basic concept of cache, I think replacement policy, partitioning, prefetching, all these concepts are already discussed in this FDP. The concept of NOC, how NOC work, what are the routing algorithms, what is called hardware Trojan, and all these things are also already explained in
Shirshendu,
this FDP.
sorry for the interruption. I think the prefetching part hasn't been covered. Probably, you can spend a few minutes on that if time
Okay.
permits.
Okay, thank you. So
Yeah,
I'll cover it on day two. So if time permits, maybe quickly I'll cover it today. Otherwise, I'll do it in part two. Okay, but for today's talk on the no, these concepts are not required. These basic concepts are required for part two. That's why I'm requesting that please watch all the videos and try to clear this concept before the part two of my lecture. Okay, so attacks on memory. So here memory means all three types of here memory means I'm assuming only cache memory and main memory. So the main memory you normally know as the term called RAM, right? So here, instead, whenever I'll say main memory, you have to understand I'm saying about talking about RAM, and we also memory here. I'm also discussing about cache memory. So cache memory and main memory, these are the two memories that I'll discuss here. And inside the cache memory, there is a term called NOC, right? Network on chip. So I'll also discuss about network on chip or possible attacks on network on chip. So what are the different types of attacks possible in memory? So here I have classified it in, there are three categories here. Attack to steal some secret information. So before discussing these different types of attack, let me explain this first diagram here, the top diagram. So top diagram say is a multi-core architecture, or it's a multi-core processor. Here you can see there are two cores. These are cores. So assume that this is core one, this is core two. Both the core has their own private L1 cache, and both share a common large size L2 cache. L2 cache here we have written LLC means last level cache. Since the L2 cache here is the last level cache, so I've written LLC here. So you know how a memory works, right? If core wants request for a data, then first we will search it in the its own L1 cache. If it's a miss in own L1, then it will go to the last level cache here, and you can see the last level cache is shared cache. So if you see the first type of attack, that is an attack to steal some secret information. For this, you can suppose you have we have to suppose you can consider that in core 2 there is a secret application is executing, and in core 1 there is a attacker application is running. So somehow if this attacker application, if somehow this attacker application can steal the secret information, or say from the application, secret information from the application that is running on core 2, then these types of this and then this type of attack falls in this category, first category. That's where it is written that to steal some secret information. So to do this, the two well-known attacks are called side channel attack and covert channel attack. So both these two attacks, side channel and covert channel, are used to leak secret information from a secure core to a application which is running on a different core. Okay, so I'm not discussing it in more detail because most probably in day 4 there is a lecture on side channel attack, so your concept, your basics will be clear in that talk. And if not, then I'll explain it again on my second part. Okay, now the second category here is attack to degrade the performance of the system. Here the attacker is not trying to steal, actually not trying to steal anything. It is its main intention here is just to degrade the entire system performance. So here some of the attack is called DOS attack that we already know, denial of service attack. We'll know it from our network course, hardware trojan in NSC. So an example of DOS attack is, suppose here in this core C1 there is the application running. So intentionally what this application can do, it can request some particular block in such a way that uh, it can remove all the blocks that is residing here in last level cache of C2. Or suppose here there is the application running called A1 and there is the application running called A2. Both the application are sharing this LLC. So A1 and A2 both applications data are there. So now if A1 knows the how LLC is managing the data of both A1 and A2, then what A1 can do, A1 can send a specific stream of data in such a way that it can remove all the data of A2. So if it do so, there is no correctness issue. It is not stealing any information, but it's still degrading the performance of A2, right? So this is a kind of DOS attack. So and if you remember yesterday's Dr. John presentation, then he has explained this type of diagram. So I hope you understand this is a NOC and the basic concept of NOC is already explained. So assume that this is a hardware trojan. So if this is a hardware trojan, what it can do, it can intend, suppose there is a packet going through this router. So this router can duplicate this packet and maybe the original packet will be sent through the destination, but at the same time it will duplicate this packet and it will inject this duplicated replicated packet to the network also. So if it do this, then it will increase the collision in the network, and it increase the collision means it is reduce the performance. So that's why I say this here the attacker tries to degrade the performance of the system. The third type of category here is attack to make incorrect execution. Incorrect execution means here it is not, maybe it will not degrade the performance, it will not steal any secret information, but still it will do something such that the actual execution will not be correct anymore. So one very good example I can give from the yesterday's presentation that Dr. John has given is, suppose this hardware trojan has the capacity, has the capability to modify the data passing through this router. So in that case, suppose there is a packet passing through this router, it can if it flips 2-3 bits, then also the entire packet will change. So if you assume that if it is an important transaction going on and the data that is going through this router and this router has changed 2-3 bits, then entire everything will be corrupted, right? So this is one type, is an example of incorrect execution. Another incorrect execution is called raw hammer attack, and that we will discuss in more detail today. So I am skipping it. So you can see these. What I can say, the attacks that is possible in memory can be categorized, broadly categorized in these three categories. Now, how to handle such attack? Two things are required for countermeasure. First, detection and mitigation. Detection means, first of all, we need to detect that the attack is going on, because all these attacks are dynamic. Dynamic means when you have designed the computer, there is no such, you cannot detect any attack at that time. These attacks activate dynamically when computer is running. So first thing is detection, how to detect this attack, and then once the attack is detected, how to mitigate or how to remove this attack, how to handle this attack. So these are the two things here. But the challenges here is when even for detection mechanism or for mitigation mechanism, you cannot propose a very complicated mechanism, because what normally happens is most of the mitigation technique or detection technique, mainly mitigation technique, reduce the performance, because most detection techniques works in background, they don't fall in the critical path because they analyze the behavior in background. But once it is detected, then the mitigation technique is implemented in the for front end. Front end means whatever you will implement for mitigation, it affects the critical path. So it has been found that most of the mitigation technique degrade the performance, and that's why it is still a very important area of research. Otherwise, almost all the attack you can see here, for all the attack, there is a mitigation technique exist, there is a detection technique exist. But why we are still working on it, why it is important? Because proposing a performance efficient mitigation technique is still going on, and that is the challenge, and that's why most of the research is going on. But the possible research direction, there is one more possible research direction, is called proposing new attack. Proposing countermeasure, I think I have already covered. Proposing new attack is also a possible research direction. But maybe there is a question may come here, that why to propose new attack, why to act like a villain? So see here, if you propose a new attack, you are not acting like a villain. So if you don't propose, you are not proposing, you are just exposing an attack, a possible attack which is already, there is a possibility of attack. You are just expo means you are exploring it, and it's saying, see, this type of attack is also possible. If I'll not explore it, then maybe some attacker will explore and it will hack the computer in future. So proposing a new attack means you are just showing the world that, see, this type of attack is also possible, and we need to work on it, we need to handle this attack. Otherwise some attacker may use this technique in future and attack our computers. So in these two directions the research is going on, and as I said, I'll try to motivate you all to start research in this direction. But if we see that who are the people who are working or doing research in hardware security or memory security, then you will see that the people who are working in this area are already working in, what you can say, computer architecture. So you can see all the speakers here in FDP, they are either working in hardware security or memory architectures. So if you want to work in this area, then you must have a basic knowledge of memory systems, how memory works. This is very important. And yes, some advanced level concept is also required, which is not given in any textbook. Why? Because the more you know about microarchitectures, then more you'll be familiar about this. Because if you don't know how a NOC works, you cannot propose a new attack. If you don't know how a NOC works, then you cannot mitigate a attack that is going on NOC. So it means that first you have to understand the complete concept of NOC. Then you have to understand that what are the recent research going on to improve the performance of NOC, to reduce the energy consumption of NOC. The more you will survey on this, then more you will understand, and more and the security problems will come better in your mind. So security is not a new area. You can do a good work in security only if you are spending time on other aspect of memory. So how to start? So one option is here in this FTP, you can see there are different speakers are contributing. So from all over the India. So you can directly contact all the speakers and see, you can contact with them, and then you can start from there. So if talking to our department, in our department we have 3 members. Dr. Neeraj is a senior member, and then both me and Kailan joined almost at the same time. So we all 3 works in hardware security. So you can contact any one of us. And since I am the speaker for this talk, then so let me advertise myself a little more. I have a lab here. My lab name is Cosmos, Computer System for Emerging Memory Optimization and Security. So you can see the details about my lab and my research work from my webpage. And as I said that you need some advanced level concept to start working in this area. So I'm giving you one link here that you can follow this link. I'll share this slide so that you can see this link. This is actually a link of playlist. There are multiple videos are there in YouTube for memory systems. So starting from replacement policies, prefetching, and there are and main memories also. There you will not find any videos here on security, but the advancement going on cache memories and NOC, these are available in this playlist, and I think it is important. So this is just an option. You can also follow other researcher, and so the main point here is you should know what are the advancement going on to improve the performance of NOC, the performance of main memory, the performance of cache, reducing the energy consumption. All these things are important, because the more you know this, then you'll be better prepared for working on security aspect of memory systems. Okay. So now I'll start with memory. What is memory? So the device that store information is called memory. That is well known to anyone, or we can say the device that store data is called memory. Two types of memory, we know, volatile memory and non-volatile memory. Technologies are some technologies I have also mentioned here: SRAM, DRAM, and NVM flash, etc. This is a figure is called a hard disk, pen drive, main memory, or RAM. So here the first two, that is hard disk and pen drive, are volatile memory, non-volatile memories, and RAM is a volatile memory. I hope you know the difference, so I'm not explaining it here. So now let us start with the real picture of a computer. So we all know that almost all the computers follow the von Neumann architecture. Von Neumann architecture means initially all the data is in memory. So when I'm saying about memory, I'm considering hard disk, RAM, cache, everything. So I'm not distributing them. So assume that there is a memory. So initially all data is in memory. And if processor want to perform some operation, then data will be moved from memory to processor, and then processor will execute, perform some operation, and the result will be returned back to the memory. So in real computer, there is a processor here. Inside this fan, there will be a processor. We store RAM here, right? And this is the hard disk. Okay. Now, the main issue here is main challenge here to design a memory is how to store information. So we all know that in computer, information or data means the binary representation of the data. So no matter it's a movie, it's a data, I mean it's a text file, or it's an image, ultimately we have to store it in a digital format, like the combination of 1 and 0, 1 and 0, right? So the main question here is how to store 1 and how to store 0. So suppose, assume that if this circle is a hardware module which can store 1, and this square is a hardware module which can store 0, then if you want to store a big string of binary 0 and 1, then I just use these two module multiple times, right? And that will be enough to store. So the main question here, that is, as you have see here, you can see here the technology means there are different technology. The technology varies on the concept that how to store a single bit of information. That is how to store a 1 bit of information. And this technology to store 1 bit of information varies in SRAM, DRAM, NVM, flash, etc., etc. So here in this talk, I'll mainly concentrate on DRAM. Why DRAM? Because most of the main memory today are designed with DRAM. So even the attack that I will explain today is also mainly possible on DRAM, though it is also possible in NVM, but mainly possible on DRAM. That's why let us start with DRAM. This technology which is used to design all the modern RAMs. Okay. So as I said, how to store 1 bit of information. To store 1 bit of information, here the module that need to store 1 bit of information is called a cell. So this is a cell for DRAM. So in this cell, you can see this is a capacitor. This is a capacitor, and this is a transistor. This is a transistor. So what capacitor do is, here you can store some charge here. Suppose this capacitor is fully charged. Assume that fully charged means it is binary 1. So if it is binary 1, then how we can read it? To read it, you have to activate this red line. If you activate this red line, then this transistor will on. The transistor acts as a switch. So if this transistor is on, then this charge will be available through this bit line. And if this charge is available through this bit line, then there will be a separate device. It will sense this charge, and it will check. It will say that okay, it is a binary 1. Okay, and if it wants to store binary 0, then there will be no charge stored here, and in that case when you will activate this row, then there will be no charge flow here, so that will be sensed as binary 0. So the I'm explaining it in a very basic way. There are some hidden concept is there, but I'm ignoring this. So assume that if the capacitor is fully charged, then I'm assuming it is binary 1. If the capacitor is not charged, I'm assuming it as 0. It may be the opposite way also, but just assume it. So in that case, suppose I want to store 4 bit of information, then I need 4 cell like this. Okay. So and now assume that these two are fully charged. So in that case, this particular memory at this moment representing 1001. Okay. So now if you want to read this, then what you have to do, you have to activate this line. If you activate this red line, this is called a word line, then all this transistor will be on, right? So if all this transistor will be on, then the power or the charge that is stored in the corresponding capacitor will be available through these bit lines, and there will be a sensor which will capture this charge, and it will sense whether this means binary 1 or binary 0. So this is the main concept of DRAM cell. And if you want to design a 10 GB of DRAM or a 100 GB of DRAM, this small basic unit will be just replicated to design it. Okay, so now what is the difference between this DRAM cell and SRAM cell? If you go for a SRAM cell, then in SRAM cell, a capacitor is not required, but in that case, 6 transistors required. But here in DRAM, you can see only 1 transistor and 1 capacitor is required. So density wise, DRAM cell is better. Density wise means suppose this is your chip area. So in this chip area, if you can place 4 MB of SRAM, then you can place at least, I think, at least 40 MB of DRAM. So density wise, DRAM is better, but yes, it has some disadvantages. One disadvantage you all know that it is slow compared to SRAM, because SRAM are used to design cache memories, and obviously we know that RAM is slower than cache memory. So I'm not going to these details because these are different concepts. There is one more important disadvantage of DRAM is since we store information or data in the form of charge, after some time this information will automatically discharge if we don't refresh this capacitor. That's why after a certain interval of time, that is called refresh interval, we have to refresh those capacitors such that the information should be there. Otherwise, if we don't refresh, the data will be automatically discharged. So this is also not required in SRAM. So there are advantages and disadvantages, but in DRAM, but since it is economical and also it is area efficient, all the main memories are designed with DRAM. Now let us try to understand the DRAM architecture in more detail, or what I can say that let us try to understand the structure of a RAM that we normally use in our desktop or laptop machine. So let us start with this computer. This is a desktop computer. The processor is here, and we put RAM in these 2 slots, and this is hard disk, right? So these 2 slots are actually showing here. These 2 slots can be either in the same channel or maybe distributed in the 2 channel. One channel means they are using only one bus, and 2 channel means there are 2 separate bus to communicate with the CPU. So maybe assume that these two slot here using the same channel, no problem. But if I go to a computer shop and try to purchase a RAM, then what I will purchase, I'll purchase this type of thing which is called DIMM. I'll purchase it and I'll put it in this slot. So there are in this computer there are 2 slots available for RAM. So you can say I can insert 2 DIMM here. So that part is clear because it is clearly visible, because if you can purchase, you'll purchase a DIMM. So let us start from DIMM. If we start from DIMM, then this is a DIMM that we can purchase, and you can see this has 2 sides, front side and back side. Both sides look similar. So each side is called a rank. So that's why you can see here rank 0 and rank 1. So just concentrate on one side. So assume that the front side is rank 1. So I'll concentrate on rank 1. So in rank 1, there are multiple chips. Which are the chips? You can see there are some black rectangles visible, right? So these black rectangles are called chip. So there are 7 chips here. So concentrate on this diagram now. This is the diagram of a rank. Why I'm saying rank? Because I'm only saying about the front side of this DIM. The same thing is also there in the back side, which is called rank 0, suppose. So in this particular rank, there are 7 chips. And why it is called rank? It's called rank because if you give a command to this rank, then all the chip here will perform this same command simultaneously, like a rank of an army. So if you give a command to a rank of an army, all the army person will execute the same command. So the same thing here is, if in the rank, if you give a command, that same command will be executed in all the chips simultaneously. So for example, suppose the cache is requesting for a 64-byte block. If there is a miss in last level cache and the block size is 64 byte, then that request will be there in main memory. So suppose that 64 byte, how it will serve? Maybe the first 8 byte from chip 0, then next 8 byte from chip 1, then last 8 byte from chip 7, and the total, the 64 byte block will be transferred. Okay, so this is how chip works. So now let us read these 3 points. And a DRAM-based main memory consists of multiple ranks, chip, and bank. I hope this part is clear now. A DRAM-based main memory consists of multiple ranks. I'm only saying about DIM. A DIM has multiple ranks, then chip and bank. I hope this, up to this, it is clear. Okay, I have not shown you bank yet. I'll show it here. How up to this point, I think it is clear, as rank has multiple chip. Now how a particular chip look like? This is the internal structure of a chip. Chip has multiple banks. So bank 0, bank 1, bank up to bank 7. There is 8 banks there. So you can see all the banks within a chip share the same common bus here out to communicate with outside. So now let us redo the rank. So this is the actual figure of a rank. So try to understand it. You can see in this rank there are multiple chips, and each chip has multiple bank, right? I hope up to this point it is clear. Now there are 2 questions. First question may arise. First question is, why we are dividing it into multiple chip? The main reason to divide into multiple chip is to reduce the cost, because it will reduce the number of pins in the chip, so it will reduce the cost. This is the first reason. Now the next question is, why we are dividing it into multiple banks? Why not a single bank in a single chip? That is because of increasing the parallelism. Why parallelism? Because if there are multiple banks, then all the banks can execute or perform some tasks simultaneously. But again, the next question is, if they are executing, they are capable to execute simultaneously, then why they are communicating outside world with a single bus here? You can see there is a single bus. Then how they will work in parallel? This is because whenever you will send a request to a bank to read the data of within the bank, there is some internal processes there. So that internal process can be performed in parallel. For example, suppose if you are requesting a block in this time, and suppose this time is for internal processing in bank, and then this is the time for communicating. Okay, so this is first request. If there is only single bank, then next request will start from here, and this will be the time taking inside the bank to process the data, and then this will be the time taken to communicate. But if you have 2 banks, and assume that the 2 requests are going to 2 different banks, then first request will perform as it is, second request will also start from here, and it will perform, because these work will be performed in 2 different bank, and they can perform in parallel. And then in this time, the first bank will the first data will be transferred, and in this time the second data will be transferred. So in this way you can reduce the time. So that's why a chip is normally divided into multiple banks. I hope up to this the points are clear. And now the next is how a bank should look like. Each bank has this type of structure. So I think this design is clear to you. This is a DRAM cell. So in each bank there are multiple DRAM cells arranged in rows and columns. So you can see there are 4 rows and multiple columns here. Okay, So if you want to read a data from a particular cell, what we normally do is we first activate a particular entire row. Then the content of the entire row will be available to this module. This is called a row buffer or sense amplifier that I will explain in next slide. So just here, it is enough to understand that if you want to read a particular module from a particular cell, then we'll activate the row. Then the content of entire row will be available in row buffer, and from that row buffer we can read it. Okay, so now let me revisit. Okay, it's the important point here. The diagram that I'm showing is still not the complete diagram. It's still a simplified diagram. In reality, a bank is also divided into multiple sub-arrays, and each sub-array has their own row buffer. But I'm not including all these things. I'm trying to make this design simple. Okay, so this is a quick recap that what I have explained till now. This is the actual diagram of a computer. Now, if we can install multiple RAM or multiple DIMM on it. So now, if this is a particular DIMM, it has two sides. Both side is called a rank. So now, if we concentrate on a particular rank, then this is how a rank look like. There are multiple chips. Each chip is divided into multiple banks, and each bank looks like this. So what I'll recommend you here that you can take a screenshot of this. Why I'm saying screenshot, because when we'll take a break for 10 minutes, at that time you can quickly check this diagram. So that because this diagram or the concept will be required in the second part of this talk. Actually, the first one is second hour of this talk. It will be required. So I hope this, whatever I've explained, so you can see all the top down from your channel, DIMM, rank, chip, bank, row, column, and DRAM cell. Everything is clear. So till now I have only explained the structure of a DRAM. Now I'll explain you how this DRAM performs some operation like read, write, and refresh. All these operations, how those operations happens in a DRAM, that I have not explained yet. I've only explained the structure, and I hope the structure is now clear to you. Okay, then let us move to next slide. In this slide will explain the basic DRAM operations. So
Dr. Shirshendu, there are a couple of questions in the chat box. If you want to take it later, it's up to you.
No, actually, in my tab it is full screen mode. So
okay.
So let me check in my desktop. Is it possible to access bank X of one chip and bank Y of another chip? Okay. See, if I go for traditional approach, as I said in rank, if you give one command, the same command will be executed in simultaneously. So in that case, normally we assume that if bank 0 is accessing in one chip, then the same bank 0 will be accessed in another chip also. But there are a lot of research. There are different things. For example, suppose in chip 7, a particular bank is not acting properly, or maybe it is affected with process variation and all. So there are many research worker there where the content of one bank is moved to another bank. So if this type of internal mapping is there, then it may be possible that in chip 0, bank 0 is working, and for the same task in chip 5, bank 6 is working. It may be possible. So this is, as I said, this is just a beginning, but if you do more research, you'll find that many other alternatives are also possible. So what is the size of each bank here? Size of each bank is varies depend on normally the in the one row we store I think 8 KB. So its size of banks varies. So at this moment I cannot say the exact or the standard size, but yeah, it varies. Any other comment? I think these are the two comments. Okay. So as I said, whatever I'm explaining is very basic thing and also very simplified way to understand. So this may be not followed by all the recent DRAM design that is available in market. But if you understand the simplified design, then you will also understand the other design. That's why I said, if you want to start a research in this area, then at least 2-3 months is required to prepare all these things. So this after this you will just get a basic idea of how DRAM memory is structured, but that is not enough. This may be very simplified structure. As Dr. Biman is saying, he is correct. There are many other researches going on where we'll remap the data from one bank to another. So, but this is again this itself a huge area of research, so that I cannot explain all the details here. Okay. So operations in a memory, any memory, if operation means first operation means read and write. How to read the data, how to write the data here. So first I'll try to explain here how to read a data. So let me number this row 1, 2, 3, 4. Assume their columns are also numbered starting from 1. Okay. So suppose I want to read the content of cell number 1, 1. For example, this cell. I want to read the content of this cell. Sorry, it is 2, 2. Okay. So now how to read it? First, we will activate this line. We will activate this line. So if we activate this line, then how or what actually happens? Activate means this word line will be activated. This word line will be activated. If this word line is activated, then all the charge available through these capacitors will be available through this corresponding bit lines. Okay, so these charge will be visible to this amplifier module, sense amplifier module, that I'll I'll discuss after few minutes. So in this way, once you activate this, the charge available to this capacitor will be available here in this row buffer, and this row buffer will amplify it to either binary 0 or binary 1. So once you activate this row, the contents are available in row buffer. Now if you want to read multiple column, then you can read it from the row buffer. So suppose if I want to read 2, 2, then first time I need to activate. Now the data is available in row buffer, so I can read second column. Now if I want to read 2, 3, activation is not required because data is already in row buffer. I'll simply read the third column from this row buffer. So I hope you understand. But now after this, if I want to read 3, 1, then it's a new row. That content of that row is not available in row buffer. So I have to activate a new row and first move the content of row 3 to the row buffer, and then I can read it. So this is how the activation and column read normally happens. So I'm explaining it in very short with a very short description, because there are some internal concept I'm ignoring here. Now pre-charge I'll discuss after a few minutes. So before pre-charge, let me explain about DRAM refresh. That I have already said that the charge information stored here in form of charge, and they may destroy after some time. So you have to refresh it. So for this, you have let us consider this diagram here. If you refresh a row here at this point, then at this point, assume that this is time. So at this point, you have to refresh it again. This time is normally called retention time or refresh window. Most of the time, we consider it as 64 milliseconds. So it means that if you are refreshing a row now, within 64 milliseconds or after 64 milliseconds, you have to refresh the row again. If you are not refreshing the row after 64 milliseconds, then the content available in this row may discharge, or if the capacitor discharge, then the information stored will corrupt, because if there is a binary bit 1 and this binary bit is flipped from 1 to 0, then the entire data is corrupted, right? So this is called, so you have to please remember this term called TRFW. It's actually the time for refresh interval or refresh window. Memory controller means all this command that I'm saying, that activate this row, okay, then send the which column need to be refreshed, then need to be read, then which row need to be refreshed, at what time it need to be refreshed, who manages all these things managed by a module called memory controller. So again, I'm not going in detail because only the basic concept is required here. So I hope what is called retention time, refresh window, memory controller is clear. Now row buffer and sense amplifier. What is this row buffer and sense amplifier? Normally let us concentrate on this zoom diagram of a DRAM cell. Here you can see this is the capacitor. Here we store the charge, and we activate this line. The charge is available through this bit line, but actually in reality this charge is so tiny that it's very difficult to guess that whether it is by binary 1 or binary 0. So for that, we need an amplifier circuit. So this is amplifier circuit. Here what I'll recommend you, that first you ignore this part and only concentrate on this. This is an amplified circuit. So this is a very simple property here. Suppose this amplified circuit is in half VDD mode. In both sides it is half VDD. in this state, if you there is a single slight increase in the voltage in the top side, then it will move to VDD here. So this is the property. So suppose it is half VDD, half VDD, both sides same. Now after some time, if this side has half VDD plus delta, slight increase in voltage, then automatically it will be moved to this stable state, that VDD this side and 0 this side. And the reverse is also true. Suppose both side it is half VDD, half VDD, but somehow if the lower side has little bit more VDD, or this side has VDD minus delta, means this side is higher, then it will automatically goes to a stable state where lower side will be VDD and upper side will be 0. So there are two stable state here. Once upper side VDD, lower side 0, another stable state lower side VDD, upper side 0. So you can represent one stable state as binary 1, another stable state as binary 0. So now let me show you how it's perform the read from a DRAM cell. Suppose this is the DRAM cell and this is the transistor. So if whenever we will activate this transistor, so this transistor will be on like this. So here the transistor is on. In that case, what will happen? Now assume that the capacitor is fully charged. The moment you switch on the transistor, some charge will be available through this bit line. And if some charge is available through this bit line, then that charge will be available here. So now that's what that charge will make. Initially, your sense amplifier is in half VDD, half VDD. When you switch on this transistor, some charge will be available here. So the upper side of this will be half VDD plus delta, the charge, that tiny charge that is coming from your DRAM cell. So it means that according to the property of sense amplifier, automatically this will be converted to this stable state where this is VDD and this is 0. So this represent binary 1, suppose. And also remember that at that time when you initially activated this, some charge, the charge from this is discharged, right? Because this charge is available here. But since the switch is still on, when this will become 0 and this will become VDD, again this charge will be recharged, this cell will be recharged. Okay, so now let us understand this here in this big picture. When I'll activate a row here, when I'll activate this row, what will happen? This charge will be available through this bit line, and this bit line will now, this sense amplifier is already in a half VDD mode. So based on this bit line, this sense amplifier will either go to stable state 1 or stable state 0. But doing this, these charge contained in this tiny cell will be discharged for some time, as you can see here. But since it is already in VDD and switch is on, after some time the charge will be again restored here. So this is called restoration time. So after activation, restoration needs some more time. This is called restoration time. Same thing is also true for if this cell is empty. So I'm not explaining this. I have only explained how this sense amplifier sense when there is a this capacitor is fully charged. Okay. So now I hope you understand the purpose of sense amplifier. But the sense amplifier circuit is complicated and it's a costly circuit. That's why we use only one amplifier for a sense amplifier for all the cell stored in a column, not for its one sense amplifier for each cell is not possible. So that's why only one row can be activated at a time, because you cannot activate two rows, because activating two row means two cell per column you need to activate, and that is not possible because there is only one sense amplifier available for each column. So I hope now sense amplifier is clear. Now pre-charge concept will be clear. What is pre-charge? Pre-charge means, suppose as I said previously, that suppose first you have requested for 2,1. So row 2 is now available in row buffer. After some time, if you want to read 3,2, so 3 is a new row. This row is not available in row buffer. So first of all, you have to activate row 3. So to activate row 3, to activate any row, your sense amplifier must be in half VDD mode. So converting all these sense amplifier into half VDD mode is called pre-charge. So sometimes people think like that the pre-charge means writing the result back to the row. That is not correct. Writing the result back to the row is a part of restoration process that I have already explained. Pre-charge means just sending what you can say, making the sense amplifier in half VDD mode such that we can activate a new row. So I hope these basic concepts are now clear. These basic concepts are required for. There are many other concept commands that I'm ignoring here because of time. So now I'll quickly explain how. Okay. I forgot one important point, refresh. how refresh happens. I've explained that within a particular time we have to refresh each row, but how will refresh? What a specific operation that we need to do for refresh? Nothing new. If you understand this activation and automatic restoration, then you will understand that for refresh you just need to activate a row. If you activate a row, then automatically the row will be available in row buffer, and after some time automatically will be restored. So refresh हो गया, refresh done. So if you want to refresh a new row, then before refreshing a new row you have to pre-charge it, otherwise you cannot activate. So refresh means activate, pre-charge, activate, pre-charge, activate, pre-charge. If you do this combination, then you can refresh all the rows one by one. But now if you have a rank like this, I hope you are understanding this is a rank, there are only 4 chip and there are multiple banks here, then how to perform refresh? In that case, what is actually happened in memory controller will send a refresh command first. So when memory controller will send a refresh command, that command is not to refresh all the rows within a bank. Suppose the first refresh command will refresh the first 4 rows of bank, so that will be performed simultaneously in all the chips. The first 4 row will be refreshed when the first refresh command will come. So suppose that when the first refresh command arrives, then the first 4 rows are refreshed. So this time is called TRFC time. After some time, again another refresh command will come, and that refresh command will refresh the next 4 rows here in each bank. Okay, and between this time is called TRFI time, the refresh interval time. After this, the next 4 will be refreshed. Then after that, another refresh command will be here after TRFI time, and this refresh command will refresh the remaining 4 rows. So each refresh command takes TRFC time, and it refreshes fixed number of rows. Okay, and this way it is refreshed the entire thing, and these things will be repeated in every refresh window. So in every refresh, suppose there is a row here and refreshed here, and again it is refreshed here, another row may be refreshed here and will refresh here. So the refresh interval is overlapping. I hope you are understanding it. So now where is the problem? Why refresh? What are the you will see, reducing the refresh operation, reducing the refresh overhead is a major area of research. Many people are working on it, and if I start talking on this particular topic, then I think it's need entire 2 hours to discuss that what are the recent advancements are going on to reduce the refresh overhead of a DRAM. But the question is, what is the where is the overhead, and why we need to reduce the refresh? The first point here you'll understand from this, that when the first refresh command arrives, it is refreshing one by one all the rows, first 4 rows here, right? How refresh command performs? Refresh means you are activating a row, and then you are pre-charging it, then you are activating another row, then pre-charging, then activating another row. It means that your bank is busy doing refreshing. So at that time it cannot perform any normal operation. Normal operation means reading and writing. So no read write possible at this time. So this time is called blocking time. So your DRAM is blocked this time. So it is reducing the actual activation time of a DRAM. This is the first point. Second point here is, it is also consuming some energy, because you are performing some operation, right? So you are performing some operation means consuming some energy. So refresh operation consume a significant amount of energy in the DRAM chip. So that's why there is a lot of research going on to how to reduce the overhead of refresh, how to reduce the blockage time and all. So if you are interested, you can search it over internet. You will find different types of command works, and people are still working on it, and this is also a very interesting area of research. But since today we have to discuss on security aspects, so I'm ignoring this part. So I hope all the concept that I have explained till now is clear. Okay, so I'll stop here, I think. So I'll open for questions, because think we have 5 minutes for the question and answer. So I'm stopping here. I hope all the concepts of basic concept of DRAM is clear. So if you have any question for up till now, then you can ask. Okay, I think there is. But I've requested you to take a screenshot of this. Why? Because this diagram may be required in the next hour. Because when I'll explain the attack on DRAM, I'll use the concept of cell, row, refresh window. All these things will be required. So I hope these concepts are clear. What is called refresh window, what is called refresh interval, then activation, bang, cheap, row. All these concepts are clear. So based on this, I think we'll take a break for. We have started on 11:05. Dr. Kalan, when should we start again?
I'll leave it to you. Your call.
Now is 11:03 and there is no
Yep.
questions from the audience. So maybe we can start from 11:10.
Sure.
Okay, then we'll start from 11:10.
Okay. Yeah. Uh, thank you, participants. So we will have a small break now. We all will meet at 11:10. I'll continue. Uh, Meaning I'll not close this meeting link. It will continue to be active. Thank you. Hello, everyone. Welcome back. So, Dr. Shirshendu, we can start whenever you are.
Yes, thank you.
Yeah, thank you.
So the basic concept of DRAMs are already discussed. So now, as I mentioned in my first slide, that today we'll discuss about important attack on main memory. So now I'll discuss about important, a well-known attack called row hammer attack. This understanding this attack is very simple. So this first slide is enough to understand the complete row hammer attack. So what is row hammer attack? Aggressive activation of a row within a refresh period may flip the bits stored in the adjacent rows. This is called row hammer attack. So suppose this is a row that I am showing here. This is a particular row. This suppose this row is activating aggressively, means multiple times. So how it will activate? For activating this particular row, this will activate the word line, and after activating the word line, the information will be sent to the sense amplifier, and after some time, the data will be automatically restored back. So when we activate a row, as I have already explained, when we activate a row, the content of this cell are discharged, right, for some moment, and then when it is available in sense amplifier, after some time, it is again restored back. So if you continue this process aggressively for a particular row, then what happens? That it may happen that the bits in the adjacent row may flip. So this is called row hammer attack. So again, I will repeat it because this is exactly this is the row hammer attack. So this main concept I'll explain again. If a particular row, suppose this row you are activating multiple times again and again within a particular refresh window, then it may be possible. It may be possible that the adjacent row will be discharged. The content of the adjacent row will be flipped, not discharged. It will be flipped. Means maybe some of the bits may be converted from 1 to 0 or 0 to 1. It may be possible. So this is called row hammer attack. So to understand it in more detail, so okay, so this is first introduced in 2014, and you can see the reference here. I'll advise you to read this reference paper, or you can also search row hammer in Google. You will see there is a wiki page which is explaining all the details of row hammer. So first, before trying to understand in more detail, we need to introduce. I need to introduce some terms. Okay, the row that you are aggressively activating is called aggressor row, and the rows which bit may flip because of this aggressive activation are called victim rows. Okay, aggressor row, victim row is clear. Now, to understand next 2 points, that is hammer count and refresh window, you need to understand one important point. One important point is, suppose there is a row here. Suppose the aggressor row is activating here aggressively. So we know this is the refresh window. Means after this time, suppose this is 64 millisecond. After 64 millisecond, every row will be refreshed. So suppose aggressor row is aggressively activating with an intention that to flip the bit of the nearby rows, victim rows. Okay. But suppose before completely discharging a cell content, if the victim row got refreshed here, then once the row is refreshed, then it will be automatically recharged again. So if for a attacker, if his intention to attack a particular row, then that attack must be happen within the refresh window. Means when the refresh window start here, suppose this is the aggressive row, this is aggressive row, and suppose this is the victim row, this is the victim row. So if the activation start from here, then suppose activation 1, second activation, third activation, fourth, the continuously there are multiple activations going on, then before this time the bit must be flipped. After, if within this time the bit has not flipped, then in this time the victim row will be refreshed, and once the victim row will be refreshed, the charge will be again restored, right? So it means that it is very important for a row hammer attack that it should flip the bit within a fixed interval. So that is called hammer count. Hammer count means total number of the minimum number of activation required within a refresh window, which may lead to a bit flip. That is called hammer count. There's a minimum number of total activation within a refresh window. It is not possible across refresh window. If you go across a refresh window, then at this point, suppose you are aggressively activating, but in this point the victim row will be refreshed. Okay, so you have to understand this. So hammer count term is very important here. And why this row hammer happens, why this bit flip happens, because multiple voltage changes over the word line is the main reason here. So I'm not going the more detail electronic details here. So for here we'll assume that this is how row hammer attacks happens, and now we'll discuss about how to detect this attack, how to handle this attack now. Okay, but before that, what are the what are the significance of this attack? As the density of DRAM increases, the chances of having more than two victim rows per aggressor row is also increases, because as you know, the density is increased. The density increases means more and more DRAM cells are placed within a single within a die area. So the more and more cells you are placing, then the rows are getting much closer. So in this sense, if for a particular aggressor row, it may be possible that more number of victim rows are possible in two sides. And because I think as per this research paper that I'm mentioning here, that I think at max 7 in each side possible for victim rows. But it means that for one aggressor row, 14 victim rows are also possible. Okay, so now another question is how we can who can perform this type of attack. So this attack needs only by writing only a simple C program or JavaScript program. This type of attack is also possible to do. But for that, the attacker who will write this program must have the knowledge of internal structure of the DRAM, how the mapping of the DRAM, that how which data is mapping to which row. This mapping structure must be known. And then what this program has to do, this program has to request for data from the same row in multiple same row aggressively. So what this will do, this will activate the particular row aggressively. But for that, one important point is, if you remember that I said, if you activate a particular row, then that data will be available in row buffer. Next time if you request the content of same row, data will be read from the row buffer. There will be no second activation. So this part also need to, when if you are an attacker, if you write an attack, then if you are plan to aggressively activate a particular row, then before two activation you have to read something else, such that once you activate a row, data is available in row buffer, then there must be a pre-charge, and then after pre-charge, then again you have to activate. So at least you can target two rows. So there is also called a double-sided row hammer attack. There is recently proposed double-sided row hammer attack. Means suppose instead of one aggressor row, you target two aggressor row. Suppose this one is also aggressor row. So now just imagine this victim row. What will happen? First, I'll activate first row, then I'll activate second aggressor row, then I'll again activate first aggressor row. It means that hammering is done from two sides. So in this case, the victim row here, this is the victim row here, has very high chance to flip the bit very early. So both single row hammer and double row hammer are the threats for modern DRAM chips. Okay, so what are the impact for this type of row hammer attack? One impact is direct impact, bit flip. If the bit is flipped, then it means that the information got lost, right? It's a correctness issue. This is very it is easy to understand. But there are some indirect issues also. Indirect impact means latency and energy. Why latency and energy? Because when I was explaining refresh, I've told you that if you go for refresh, then at that time when you are refreshing a bank, then it is blocked for normal operation. So here also, if there is a what you can say row hammer attack going on, and somehow you have detected it, okay, someone is performing a row hammer. So what you have to do to save the victim rows, you need to refresh those rows. So this is also a time consuming process. Another problem here is a particular process program is now aggressively activating a particular row, so it means that one particular application is aggressively using this bank. So it means that maybe some innocent applications are also waiting for this bank, but they are not getting chance because one particular application is aggressively using it. So it means that there will be latency issues for other applications. This is one point. Another point is, normally it also been found that uh, if you have a DRAM memory, so the when because most of the requests are served by the cache memories, so sometimes we find some ideal window in DRAM, and in that ideal window DRAM can be switched to a low power mode to save energy. But here, what will happen if some row is aggressively activating? Then you cannot move the DRAM module to a low power mode. So here the power saving is also not possible. So that's why I'm saying energy and latency are the indirect impact of row hammer attack, and direct impact is bit flip. So I hope the concept of row hammer is clear. If you have any doubt understanding the row hammer attack, you can ask here, because then from next slide I'll try to explain how to handle row hammer attack. So is row hammer attack hidden design issue? Yeah, it's a design issue. You cannot see. There is if you have already designed a main memory, and the attack is only based on the mapping policy of row, because you cannot so that's why it is very difficult. So suppose there is main memory is already available in the market, so it's very difficult to handle it, because the attacker knows the internal mapping policy, so attacker can easily attack it. So if we want to prevent it, if we want to propose some prevention mechanism, that prevention mechanism can only implement in the new generation, or the DRAM memory that will be fabricated in future, not already available, the memory already available in market. The memory already available in market, I think, as far I know, there is no way to handle it. If there is if they have already implemented some technique, then it's a different issue, otherwise not. Okay, then let me explain how RH attack can be prevented. So as I said, any attack, there are two things: detection and mitigation. First is how to detect row hammer attack. A very basic way is use counters. Why use counters? Because to understand this, you have to understand the diagram here. Refresh window. So this refresh window, as I said, is a fixed, maybe 64 millisecond, or suppose 128 millisecond, but this refresh window is fixed. If this refresh window is fixed and I have also explained you the activation, right? Once you activate a row, and then data will be available in row buffer. This activation also has a fixed time, that I have missed that time because it was not important, but that activation time is also fixed. So if the activation time is fixed and this refresh window is also fixed, then the total number of activation possible within a refresh window is also fixed, isn't it? So assume that if this is 64 millisecond, the total number of activation possible within a refresh window is, suppose, 1024. Total number of activations is 1024. So it means that to fit a blip, to fit a flip a bit, maximum activation should be 1024, right? But if we allow to activate a particular row within a refresh window 1024 times, then it means that the bit will be flipped already. At that time, we cannot do anything. So what about if, suppose, 700? We put a counter on 7, threshold on 700, and we'll keep tracking it, that okay, if a particular, within a particular refresh window, if any particular row activated 700 times, then it means that there is a possibility of bit flip in the nearby rows. So in that case, these two rows are the victim rows, if this is the aggressor row. So in that case, it means we have detected the problem. So if we have detected the problem, how to handle it? To handle it, what we will do, we will refresh to victim rows. This is v1 and this v2. These two rows are victim rows. So we'll refresh these two victim rows. So it means that victim row, every row refresh. If I'm refreshing a row here, I'll only refresh it after its refresh window, right? But in case of v1 and v2, what we need to do, we have to refresh it once here also. Why? Because if we don't refresh it here, it will not last till this point. Somewhere in this point, the bits will be flipped. So this is a very simple technique. Like detection is also very simple. For every row, maintain a counter, and if the because this value is fixed, so put a lower value like this, 700 or 600, and once the value reaches this point, refresh the neighbor rows. So that is a very straightforward solution. That's why I said at the beginning that most of the attack that we'll discuss, there are solutions, there are detection techniques. But the problem here in this solution, in this counter-based solution, or that I have written here as a baseline solution, is you have to maintain a lot of counters, because if you calculate the total number of rows in a real DRAM is very huge, and if you try to maintain counter for all the rows, and then also periodically checking all the rows, then the circuit required for this and the total storage required will be very huge. Hardware overhead will be very significant. So that's why that is not a practical solution. We need to think something else, and that else open this area for research. There are a lot of research. I will discuss some research already done in this area. There are many interesting proposals already available, but still that point, that there is a significant hardware overhead to handle this technique, that point opens this area for the research, that it is still open there to propose a hardware efficient RH mitigation technique or RH detection technique. So now let us discuss some techniques here. I'll discuss twice later. First, I'll discuss this probabilistic detection. In probabilistic detection, what they do, suppose a particular row is aggressively activating, or so what they do to prevent this, they with some probability they refresh some rows within the refresh interval. Suppose a row is refreshed here, again a row will be the same row will be refreshed here after the refresh interval. So in the probabilistic approach, what they do is some probability they'll refresh rows in between also, here also. So what they because and assume that if this type of row is a victim row, and you are refreshing a victim row in between the refresh interval, so it means that the aggressor row cannot flip the bit. So these are the techniques used for probability detection. But against the again, you can assume that these are probabilistic approach. Not there are some concept of error, some margin of error is possible there. And then I'll discuss about twice. Twice is a very interesting concept. So twice is a counter-based concept, deterministic concept. Deterministic concept means they use counters, but I already mentioned that using counter is not possible for all rows, right? Because if we maintain counter for every rows, then it's a baseline design. But baseline detection is very hardware consuming, right? So what twice did, first they have explained this point that within a particular refresh window, only a limited number of activation is possible. For example, as I said, only 1024 activation is possible in a particular refresh window. So it means that at max 1024 rows can be activated, because every activation is a new is done for a new row. Then at max, how many rows can be activated within a refresh window? Only 1024. So it means that within a particular refresh window, only 1024 rows are important, other rows are not important. So what they did, they use a different technique. They use a table, they use a remapping techniques. And what they did, they use only 1024 counters to maintain to count the activation of rows within a particular refresh window. So this is the main point. Since all the rows, there is no chance that all the rows will be activated within a refresh window because of the time limitation and all. Only limited number of rows will be activated. So we no need a separate independent counter for all rows. We can use small set of counters and use this counter in different windows for activating to keep track of activation for different rows. So this is the main point, but I am not discussing this. This is not the only point. There are some challenges here also possible. So you can read this paper. It's very interesting paper twice. So what then it will the concept will be clear. So these techniques are basically detection techniques. They will detect that okay, there is a possibility of row hammer attack, but once it is detected, how to handle it. One straightforward way is just refresh the victim rows. If you refresh the victim rows, then also it will handle. But the problem here is, as I said, that raw hammer attack, as the technology is shrinking, therefore a particular aggressor row, the number of victim rows are increasing. So if we go for refreshing the victim rows, then also it is a time-consuming process because any refresh blocks the memory. So is there any alternative solution? Is there any better solution? So that's why now the mitigation technique. So in mitigation technique, I'll discuss about two interesting proposal. First one is called Crow. So in Crow, what they did, Crow is actually proposed for something else, but the main reason for why Crow has been proposed, that part I am not discussing because otherwise it will take time. So in Crow, the rows are divided into two parts. You can say in gray part there will be actual rows, and in this part, in green part, there will be some rows, reserved rows. Some reserved rows will be there in this part. This there will be no direct mapping of data. Actual rows are this. These are the normal rows, and some reserved rows will be here in green part. So now what they will do, suppose there is a row here which is aggressively activating. So if this row is aggressively activating, and suppose these are the uh, victim rows, because these are the adjacent rows. So what they will do, once this row is detected as row hammer aggressor row, these victim rows will be moved here. This victim rows will be moved here. So if this victim row is moved here, then it means that there is no rows here, there is no rows here. So it means that even if this row is aggressively activating, it cannot flip the bit because there is no bits here, because these rows are already copied here in this region, in this region. So this is how Crow handles row hammer attack. So again, this mechanism depends on a good detection mechanism. It has to either, maybe you can assume that for detecting the row hammer attack, we'll go with twice. Twice will detect a row hammer. Once the row hammer is detected, then we can follow the concept of Crow and move the victim block to the reserve location. And in that case, we can handle the row hammer attack. But yes, as I said, all the mitigation technique has some advantage and disadvantage. Advantage is clear, it can handle, right? It can remove the row hammer attack. But the problem is, as I have already said, there are limited number of rows available here. Okay, and as the technology is shrinking, I'm saying the number of victim rows are increasing. So if the victim rows are increasing, then it's maybe difficult in future to fit all the victim rows in this reserve ways and in the reserve location. This is the first point. Second point is the aggressor row is still blocking the memory, right? Though we'll move this data from here to here, the data is now moved here. So correctness wise, it is perfectly fine. But still the aggressor role aggressively activate. This role will be aggressively activated. It means that it is still blocking the memory. It's still blocking the memory for other application, and it is also blocking the memory to go into a low power mode. So it is still consuming. So the indirect impact that I have explained in previous slide, indirect impact are still there. And on top of that, there may be a possibility that in future, if the number of victim rows increase, then maybe this concept will not work. Okay, so this is the disadvantage. So on also then the the RHLM is a proposal from our lab. So in RHLM, what we have proposed, that we also depend on a good detection mechanism. We depend on twice. First, we depend on twice to detect a particular row hammer attack. And once this aggressor row is detected, what we do actually, we move this aggressor row from this memory to a different memory. This is our design. In our design, this is the actual DRAM bank, and with this, there will be a small STT-RAM here. STT-RAM means it's designed with non-volatile memory that I have not explained. I think in the slide number 2, I have said there are different types of memory. One memory, STT-RAM, DRAM, and non-volatile memories. So STT-RAM is a non-volatile memory, and in STT-RAM, the chances of Rohammer attack is very rare. Though I cannot say that completely zero, but the chances of Rohammer attack in STT-RAM is very rare. So what we normally do, once we detect that, okay, this particular row is aggressively activating, so we move the aggressor row here, not the victim row. Aggressor row, suppose this row is aggressively activating, so the aggressor row will be moved here. So why we are doing this? Because if we move the aggressor row here, then aggressor row will be aggressively activate here in SRAM. In that case, this RAM, the entire DRAM is now free. So if there is, if this DRAM need to access by innocent application, they can access it. If there is no innocent application, then it can also move to low power mode. So this DRAM is now free, independent of this aggressive activation, and aggressive activation is happening in STT-RAM. But yes, there are some disadvantages of STT-RAM also. In STT-RAM, the write is expensive, but this disadvantage is facing by a attacker application, not the innocent application. This is the first point. But our policy also has a limitation. So what we assume here, because once you detect aggressor row, we need to move the aggressor row from here to here. That moving is expensive. So when we move a aggressor row from DRAM to STRAM, we assume that if the attack is started, the attack will continue for a fixed number of for certain amount of time. Means attack will continue for multiple refresh window. For example, suppose a attack started here in victim cache. So it not just in aggressor row, it not just that the attack will continue till this point and it will stop. If this is the situation, then our work will not give you give advantage. We assume that if attack has started, then attack will continue over continuously. It will happen on multiple refresh windows. In that case, when the first time attack is happening, somewhere in this point, twice will detect this attack. Okay, in this point, and in this point we'll move the row here in STT-RAM. So in next window here, when it will try to modify the block in this location, this point, at that point activation will be performed in STT-RAM. So DRAM is free at that time. So based on this assumption, our work is our proposal is working better. But yes, there is a limitation, I have already explained. And then you will see there is another proposal, the block hammer that I mentioned here. So block hammer is also kind of related with RHLM. But what this block hammer did, first of all, they try to use the detection. They use the detection technique. They don't use twice for detection. They have their own detection mechanism. So based on this detection mechanism, they try to detect a row hammer. And once a row hammer is detected, they block the access of that aggressive row for some time. Suppose this row is aggressively activating. Okay, so there will be a detection mechanism. Based on this detection mechanism, whenever they detect that, okay, this particular row is aggressively activating, they will block accessing this row for some time. So what they are doing, if they block accessing this row for some time, it means that this entire DRAM is now free for innocent application. This entire DRAM is free for low power transitions. So in this sense, RHLM and block hammer are similar, but yes, instead of moving it to STT-RAM, they are blocking it. So as I said, all this detection technique that I have explained here, all these detection techniques and all the mitigation technique that I have explained, they have advantages, they have disadvantages also. Advantages means almost all of them, excluding these probabilistic approaches, almost all of them are doing the task 100% correctly. Means row hammer is stopping, because the main direct impact of row hammer is data corruption. That direct impact is stopping by all of these techniques. But there are, the second point is hardware overhead. So almost all of these techniques have some limitation, or in some of them have hardware overheads. So that is the reason this area is still open, that proposing some row hammer detection mechanism or proposing some row hammer countermeasures with efficient harder what you can say overhead is reduced hardware overhead is still is still open area of research, and you can also work in this area. But to start working in this area, you need to do some more research. Then only you can start. This is a slide. This is a motivational slide. Motivational slide means you can see this. The graphs are taken from these two papers, 1 and 2. So in this graph, you can see the experiment has been performed in three different DRAM manufacturers. This is manufacturer A, manufacturer B, and manufacturer C. And these lines in each manufacturing, for example, in manufacturer A, you can see there are multiple lines. These lines are for different DRAM versions. And in x-axis, this is hammer count. Hammer count means, as I've already explained, the minimum number of counts required to flip a bit. So you can see here for the newer version of DRAM, the hammer count is low, means with less number of activation, you can flip a bit in the newer version of DRAM. It means the row hammer problem is the what you can say, the problem of row hammer is increasing. Why? Because you can see here also in the newer DRAM, for the newer DRAM main memories, they are flipping bit with the less hammer count. If you go for next diagram, here also you can see the hammer count needed for a row hammer. You can see all the newer version. For older version, the hammer count, high hammer count is required. More number of activation is required to flip a bit. But for the newer version of DRAM, the hammer count is less. Means less number of activation, you can flip the bits. So why this is happening? This is happening because of the technology change. The technologies are changing, and we are fitting more and more DRAM cell within a fixed area. So the density is increasing. Density is increasing, then it means the distance between two rows is decreasing. So that's why it's creating a problem. And because of this reason, if you read these two papers, mostly the second paper here, then this paper has explained that why this technique, so why this problem, that is the row hammer issue, hammer count issue, that the reduced hammer count is for the new generation DRAM, it's a warning sign. And why most of the existing detection technique that I have explained in previous slide maybe not will not work properly in future. Because, for example, the twice or RHLM, these techniques are now handling DRAM 100% accurately, right? Forget about the hardware overhead and other impact, but they are handling. But they, in this paper, they explain that these techniques may not be efficient in future because of this type of issues. This is one problem. Another problem is mitigation. If you see this graph here, this graph you can see with the newer version of DRAM, bus cycle time is reducing, read latency is reducing, but refresh latency is not reducing. Refresh latency is increasing, and the same thing is true here. You can see here. Then this is the prediction. According to this prediction, the refresh latency will increase in future. Refresh latency means TRFC time that I have explained. So TRFC time will increase in future. So it means that if the refresh overhead is increasing in future, then the directly refreshing the victim rows, or once it is detected, then we'll simply refresh the victim rows. This is also going to be expensive because overall refresh is going expensive in future. So that's why proposing a better detection technique as well as a better mitigation technique is still open for all of you. And also, I think in Micro 2021, there is a paper. Name is, I think, EUTTR, or I forgot the name, but this in micro. Let me check the name. It is, yes, UTRR. There is a paper in Micro 2021. What they did, they experimented some existing RAMs where row hammer attack handling is already there. Means RH handling techniques are already implemented in these RAMs. And what they did, they experimented a UTRR attack on this existing memory where the row hammer attack is already row hammer attack detection is already there, and they successfully able to flip the bits. So it means that the existing countermeasure that is implemented in the chip is not enough, because now more and more smart attack, raw hammer attack is now coming, and the existing technique that is preventing these attacks are not, will not be enough in future. So that's why it is still an open area, and you can also work, you can also consider to work in this area. So with this, I'll stop here. I'll wait for 5 minutes here for the question and answer. I think there is one more slide, but I think most of the concept I've already explained. So whatever written in this slide, I think I've already mentioned. So I'm ignoring this slide here. And this is the conclusion. And thank you. So this, I'll stop here. I'll stop here for 5 minutes. So if you have any question, I'll answer. Otherwise, since I have 15 minutes time, I'll quickly explain some basic concept of cache memory. Okay. There are some questions here. Even if we have no external interference attacker, we can expect such a problem. No, we have no external. No, Sham, if we don't have any external interference, then we don't have this type of problem. Why? Because we also perform experiment, and most of the normal application, like benign application, they don't have the requirement of this type of aggressive activation. Uh, see, normally we depend on different type of benchmarks. So we run different benchmarks on DRAM, and we found that for almost all the normal applications, which is an innocent application, there is no such requirement of this aggressive activation. So it means that this is unless a attacker is trying to do this, there is no possibility of this type of attack with normal application. Is the refresh window same throughout the entire RAM? Mostly refresh window is same throughout the entire RAM. Yeah, but again, I cannot say it's 100% true, because what I said is the baseline design in to if you work on reducing the refresh overhead and all, then you'll find that sometimes maybe we can change the refresh window and all, but I'll not go with this advanced level concept. So I'll go with simple design. Yes, refresh window is same throughout the entire RAM. There will be some process variation. Yes, I mentioned, I think in the first half of this presentation, that if there is some process variation, then how to handle it. And also the most another important point is the 64 millisecond that I am saying, that is not true for all rows. There may be some rows which are not that strong that it will sustain for longer time. So in that case, there are some rows also possible, which is called weak rows. So this 64 millisecond that I'm saying, it's actually considering the weak rows. Otherwise, the strong rows may sustain up to 256 millisecond. So that's why there are many interesting design possible, but these are not related to security. These are related to refresh handling techniques. So maybe suppose you can differentiate into 3 categories: very strong row, 256 millisecond, then medium strong rows, maybe 128 millisecond, then weak rows, 64 millisecond. How to handle it differently? Then is it possible to go for different refresh window? All these are interesting, and people are working on it. So strong cells are more vulnerable to RH attacks. Strong cells are not vulnerable, because if strong cell means what, they can retain the charge for longer time, so they are strong. So if a attacker is trying to discharge a strong cell, so strong means it can retain the charge longer. So again, I think this is not true. They are refreshing after a long time, fine, but they are strong enough to hold also, right? Any other questions? Since I have started at 11:10, I will continue till 12:10. Dr. Kalyan, it is okay. Is it okay?
Yeah, if you want to continue till 12:10, I think that should be okay, based on the questions and all.
Okay, so
Yeah,
I think there is no. I'll
question.
wait for 2 more minutes for
Sure.
if there is any questions. Then I'll quickly explain some basic concept of cache memory. Those will be required in my second part.
Sure, sure. Please go ahead then. Yeah.
Okay, so I think these points are already clear, but I'm trying to explain. I'll not go with technical low level details. I'll just explain everything in upper level so that you can understand. First, I'll explain cache memory. You know what is called cache memory. There is a cache memories are called on chip memory. So if there is a core here, then this there will be a cache memory here like this, and this memory is on chip, means it is within the processor. So normally cache memories are divided into multiple sets like this, and we can say this is a set associative cache. So if this is a set associative cache, there are in each entry we can store some block. So how to map? The mapping is important. So this is called set associative cache, and the rows are called set and ways are called column. So set associative cache will be very very important for tomorrow also when there are the side channel and cover channel will be discussed. So if it is not clear, please clear it. What is called set associative cache? In set associative cache, it's look like a 2D array, like the rows you can consider as set and ways you can consider as column. So how to map a block in this cache? So suppose each block has a 32-bit address. So this will be divided into first this bits will be for block offset. Suppose the block size is 64 bytes. So first 6 bits is required for block offset. And then suppose there are 1024 sets here. So 10 bits will be required for here for set index 10 bit. So now how to map? Remaining will be tag here. So how to map here? So if any block is in this core, this is the core. So if core is requesting for a particular block, and this is a 32-bit address. So based on this 10-bit, based on this 10-bit, we'll first find out the set, in which set it is mapping. Suppose the set number is 5, then we'll always go to set number 5 and search the block. This block will always map to set number 5 because of this bit. It will not go to other set. So this is the very important property of set associative cache. You have to understand it. We will not repeat it again. That's why I maybe you know it already, but still I'm clearing it. Okay. So now suppose I'm writing only one set here. So this is a particular set. Suppose this is your set 5. And set 5 A, B, C, D. 4 blocks are already there, and it's a 4-way associative. 4-way associative means there are 4 ways. Assume that there are other rows also. I'm not discussing these rows. Now in this particular set maps, set based mapping I have already explained. But now in this set, suppose there are already four blocks are already there. In this case, if the core is requesting for a fifth block, which is also mapping in this set, suppose the fifth block is called E, which is also mapping in this set. Now this set is full. So how to allocate the fifth block? In this case, we need to replace a particular block, right? That is called replacement policy. So which block we need to replace? We need to replace the LRU. If we follow the least recently used replacement policy, that is LRU, then we'll replace the oldest block. Suppose this block B is the oldest one. So what we will do, we'll replace B, and in place of B, we'll place the new block that is called E. So you have to understand the replacement policy. At least if you know LRU, then it will be enough. For any set, there is a replacement policy. So if assume that there is one more set, number 6. In this set number 6, suppose the blocks are as X, Y, Z. There is one place empty here. Assume that in this situation, the block number B is again this core is again requesting for block number B, which is mapping to set number 5. That is, this is set number 5, this is set number 6. So if block number B is mapping to set number 5, then you have to map it in set number 5. You can see that in 6 there is a empty space here, but even there is an empty space in set number 6, you cannot map B to 6. You have B to set number 5. And that's why replacement policy is local to each set. Set number 6 will have separate replacement policy, separate replacement policy. So LRU, if you understand, that will be enough for next talk. And now there is two more important point that I will discuss. One important point is shared cache. What is shared cache? Suppose we have a core called C1, there is another core here C2, there is another core here C3. There are three cores. Each core has their private L1 cache, and all the core are sharing a large size L2 cache here. And this is the shared cache. Again, it is a set associative cache. L1 are also set associative, but I have not drawn in this way. Now, if core 1 is requesting for a block, first it will request to his own L1. If it's not there in L1, then it will go to the shared core. This is the shared L2 cache. It will go to shared L2 cache. If it is not in shared L2 cache, then we'll go to main memory, fetch the block from main memory, store it in L2 first, and then we'll go to L1. So suppose C1 is requesting for a block called A. So A is not in L1, will go in L2. It is not in L2, will go to main memory, fetch the block. It is mapping in this set, so we'll map it here. Then we'll move, and block will be also placed in L1 of C. Okay, that is fine. After some time, is C2 also request for the same block. Then C2 will request for A. It will be not available in L1, so we'll go to L2 and we'll find the block in L2 because A is already there. So now C2 is also accessing this block. Both are accessing this block. Suppose in read mode. At that time, suppose C3 wants to write something to this block. C1 and C2 are reading, wants to read something from this block. Now C3 wants to write something in this block. Now, first of all, if C3 is requesting for A for writing something, there will be miss in its L1. So it will go to L2 and there will be hit in L2 because A is already there. Now at this moment, if we let C3 to change this value in L2, if we let C3 to change this value in L2, then what will happen? C1 and C2, they have also the value of A, and these values will be old. Assume that all values of A is 10. Now C3 wants to change it to 20. Now this value will become 20, this value will become 20, but these two A's will be 10. So this is not acceptable. So for that, how to handle it? So in that case, if C3 is requesting A in a write mode, then first of all, there will be a directory here. It will send invalidation request to this two. It says, see, the block that you are holding now, someone else need to update it. So please invalidate this block or please remove this block. So what these two cache will do, they will invalidate their block and send an acknowledgement here that, okay, we have removed our copy. So after that only, it will allow this cache to change the block. In that case, what will happen? When C3 will change the value of A from 10 to 20, the only copy that will be available for A is in C3. C1 and C2 will not have any more copy of A because they have already invalidated. So whatever concept that I have explained here is called cache coherence. So cache coherence is also very, very important. So maybe whatever security concept that we'll discuss in tomorrow and day after tomorrow, cache coherence concept may be also important. So maybe you can quickly go through what is called cache coherence concept, and that will I think that will help you to understand the concept in next two days. Okay, so shared cache coherence, replacement policy, all these concepts are clear. So only one concept remains, is called cache partitioning. Cache partitioning is also important. Cache partitioning means the same thing when there are multiple cores sharing a cache. Suppose the same concept I'll use, C1, C2, and C3. There are three core, all have their own L1 cache, private, and they are sharing a common large size L2 cache. It is just all cache are set associative. L1s are also set associative, but I'm not designing it in such a way, but assume that all are set associative cache. Okay, so now C1, C2, C3 all are sharing this L2 cache. It may be possible that the application that is running on C1 needs more space compared to C2, or the application that is running in C3 is a very small application. So for all this, if we simply go for LRU policy here in L2, then LRU policy may give equal importance to all the application that is running on C1, C2, and C3. So in that case, it is better to allocate a fixed position to C1, fixed position to C2, fixed position to C3. Maybe if we say that, okay, C1, you use this part, you use this part, C2, you use this part, and C3, you use this part. This is called static partitioning. You are statically partitioning the L2 cache, and you are dividing some way, giving some ways to C1, some ways to C2, and some ways to C3. This is wave-based partitioning. Okay. but this type of partitioning is not correct. Why? Because maybe after some time the demand, the application that is running on core 1 will change, or the demand of application that is running on core 1 will change. Now it needs less space, and the application that was running on C3, which was initially requiring less space, now it needs more space. But if this your partitioning is static, you cannot change it. That's why the need of it, that's why we needed dynamic partitioning. Dynamic partitioning means the partitioning that can change according to the demand of the applications. So how dynamic partitioning need to be performed, that I'll explain in next class, but at least you should know what is called static partitioning and what is dynamic partitioning. In dynamic partitioning, we partition the case based on the requirement. Okay, so this is cache partitioning, and the last concept that we need is cache prefetching. So I'll also explain cache prefetching and in this only, in this way. I am not using any technical term. Cache prefetching means, suppose this core is requesting for a block called A, and after some time the core will request another block called B. So when the core will request for A, so at that time the A will be not here. Assume that A is not in L2 also. First we will request in L2. If block is not in L2, then it will go to main memory, and from main memory will fetch A, and from main memory fetch A to L2, then A will go to L1. From L1 it will go to C1. So again, after some time, if C1, this core request for block B, then we have to process the same thing for block B also. So this is the long latency, because we are interacting with memory, long latency. Can we hide the latency? So that is called prefetching. So somehow when core was requesting for block A, if somehow there is a prediction mechanism that can predict that, okay, look, after some time this core will request for B. If somehow we can predict this, then when we will go and request for A, at the same time we'll also send a request for B, and both A and B will be fetched together and stored in the cache. So after some time, when B will be requested, such that the B will be a hit in the cache. So that is called fetching a block before requesting by a core, or before demanding by a core. So that is called prefetch. So this is the basic concept of prefetch, but this is a huge area of research. I cannot speak. In fact, a complete FDP may be possible on prefetching. That's why I'm not discussing it much. Only this concept is enough, that if there is a prediction mechanism is there, and based on this prediction mechanism, we'll predict a block before demanding by a code, assuming that this will be demanded in future. That is called cache prefetching. So set associative cache is very important. What is called block, and how we map a block in set associative cache is very important. Then replacement policy, at least LRU is important. Then shared cache is important. Cache coherence is important. Cache partitioning, and cache prefetching basics. So all these basics you please go through once, because it's very difficult to clear all these basics, because this course is for cache security, and if we try to cover this, then it's need at least one whole day. So I'm requesting all of you to please go through this concept once, such that the second and the last 2 days will be easy for you. So I'm stopping here. If you have any doubts, you can ask me. I'll be here for 5 more minutes.
So, Dr. Shirshendu, are we done?
Yeah. So I'm waiting for questions.
Okay.
But I think there is no questions.
Okay. So in the meantime, I just got to know that we need to, take the screenshots of these sessions.
Okay.
So if you disable your screen sharing, I
Just
request everyone to, switch on their cameras, so that I
okay.
can take a couple of screenshots. I hope that's okay. Um, how do I? What is the layout here? Change layout. Tiled is maximum tiles are only sidebar. Okay. Oh, I can see only a very few. Huh? How?
Huh?
How? So the layout says
Layout only.
Layout is the maximum one. This is the window size.
I think that's
so this is the
Take it.
very few, right?
That's fine. So whatever is the maximum one, take that maximum one.
Yeah. 49 is the maximum.
I think.
Yeah, but not sure. Just a couple of screenshot, guys. Okay. Now I request the ones who have switched on to switch off, and others, to switch on there, so that we get to see some, new faces. Okay.
Others are not present.
Yeah, they are showing up now. Yes. So if it's convenient to you, please switch on your. Okay. Very few. Okay. Thank you very much. We'll do this exercise after every session. Yeah. From now on, to get some screenshots so that we. Thank you, Dr. Shirshendu, for the wonderful session. You beautifully explained the basics of DRAM and emphasized the summer attack. And
Thank you. Thank you, Dr. Kalan.
Yeah. Thank you. Thank you, everyone.
Thank you, everyone.
I'm closing this link.
Yes.
I'll restart it at 1 o'clock. Thank you.
Okay.
Stop recording. So stop tracking here.